Welcome. I am John Dankanich, the Systems Capability Lead for NASA for In-Space Transportation. In this video, I will be sharing the future envisioned state and priorities to support the strategic outcome of space nuclear propulsion, which is to enable fast, safe, and efficient transportation. This is intended to be a companion video with the chart package available, as I will not be reading through the information that's been provided. This is the future envisioned state for space nuclear propulsion, which is to fundamentally enable fast in-space transits. The space nuclear propulsion prioritizes strategic investments to support an informed downselect between what is initially a parallel path development for both nuclear electric propulsion and nuclear thermal propulsion, which will be applied for future cislunar, Mars, and deep space exploration missions. Both nuclear options require maturation of a high-assay low-enriched uranium or HALEU fuel. Nuclear thermal propulsion is dependent on higher temperature fuels to meet the engine performance requirements. We are targeting to achieve at least 900 seconds of specific impulse capability. Nuclear electric propulsion architectures need increased mid-TRL funding for both large-scale high-temperature radiators and advanced thermal coatings to achieve and enable our efficient power conversion requirements, and also heat rejection solutions, which would occur throughout the operational environments. This may include potential Venus flyby scenarios, and all must be scaled to support 2 megawatt electric class solutions. System performance for either solution has a large impact on reducing crew transfer times. We recognize that significant unknowns remain prior to a single low-risk, high technology readiness level development can be warranted to meet the nuclear propulsion system demands. This is why we are currently and initially carrying parallel paths for both nuclear propulsion options. You can see here that the state-of-the-art is unfortunately significant far from the future envisioned state. For high heritage solutions, we have only flown 500-watt electric space nuclear reactors, which is orders of magnitude from the megawatt class reactors needed for the Mars transportation solutions. The thrusters are also more than an order of magnitude from state-of-the-art, even if the final architecture is an array of 100 kilowatt class thrusters. The space station represents the state-of-the-art for thermal heat rejection, again orders of magnitude below our future system requirements, and they operate at a lower temperature environment and use different working fluids than we can use for our solutions. We do have ongoing investments with a 12.5 kilowatt Hall thruster string that's in development for a 50 kilowatt electric class system on the power and propulsion element of Gateway. We are also developing a fission surface power reactor at higher power levels than our flight heritage systems. For our high-assay low-enriched uranium fuels, we have made significant progress on higher temperature performance, but have not yet demonstrated the temperatures required to achieve our 900-second specific impulse threshold. Certainly, we must also acknowledge the significant nuclear thermal propulsion work that was done many decades ago under the rover program. Also, we have subscale reactor design contracts currently in execution, and NASA would like to leverage nuclear thermal propulsion investments as appropriate that are occurring in parallel under the DARPA Draco program. We do have the terrestrial capability to produce nuclear power, but just not in the space environment and with the radiator-based heat rejection systems that we will require. The next slide here shows a high-level roadmap recommendation, which is to gain more parity between the nuclear thermal propulsion and the nuclear electric propulsion options that are under considerations to inform a future downselect. This can be seen by the Phase 1 under nuclear thermal propulsion, which includes active awarded contracts with industry and on reactor designs. Yet for nuclear electric propulsion, the Phase 1 is focused more on requirements development. The nuclear electric propulsion solution is currently receiving the fewest resources. It's highly dependent on total system alpha, or the watts per kilogram, and there are multiple technologies with unknown technology readiness level advancement degree of difficulty, as we call TRL AD squared. Development of higher temperature radiators is required for viable system mass performance. A power system and power processing unit topology will also require an IEEE parts assessment to determine if the electronics parts even exist or will require new development at the currents and voltages required within the radiation and temperature environments that are anticipated. This could potentially impact the IEEE part lead times by years. We will be identifying opportunities to leverage SBIRs for small business investments and other investment approaches as these unknowns become established. Also, early stage propulsion, for example, Hall thrusters, Vasmir, or magnetoplasma-dynamic thrusters, require investments in order to identify that AD squared, in other words, to determine if there's engineering go-do efforts or new materials and new manufacturing processes will be required for those systems. And this can also help us establish the performance expectations, including the thermal and power interfaces. We need to establish a fuel, reactor designs, and testing for the nuclear thermal propulsion, as well as the system definition and the unknown identification in order to have informed down select when appropriate. Decisions have not been made yet on what level of demonstration is required to close the outcomes. However, intermediate steps before what would be phase 4, the closure of our outcome, and for a subscale technology demonstration for nuclear electric propulsion and a subscale reactor with engine tests for a nuclear thermal propulsion option in order to have unity and parity between the two choices. The next slide here shows a near-term roadmap, which is similar information shown temporally. For nuclear electropropulsion, we will be establishing requirements and early stage designs that would inform make-buy decisions. After those decisions, we would complete the reactor fuel and moderator development in parallel with NASA and industry subsystem technology maturations in order to support an integrated propulsion subsystem test. This integrated test should provide the data to make an informed comparison to a nuclear thermal propulsion architecture. While these mainline investments are occurring, the agency will continue early-stage nuclear electropropulsion development and research contributing both analysis and on-ramps of enhancing technology solutions. For nuclear thermal propulsion, we currently have industry reactor design contracts in execution and will progress with those for a reactor critical design and a feasibility test, which should occur in parallel with government developments. This includes NASA and the Department of Energy for technology maturations, activities such as flowing hydrogen testing with sufficient fidelity to inform the architecture trade comparison with that nuclear electric propulsion alternative. Also, the NASA and Department of Energy investments will be going in parallel with the DARPA Draco efforts. After sufficient risk reduction is completed, we would move towards integrated system demonstrations, likely at subscale, again, for risk reduction prior to a cargo or crewed operational flight system development. This slide here provides a little more detail into Phase 1, which is focused on early technology investments and system requirements design to buy down the schedule and cost risk of the future higher dollar phases. There are still big open items regarding both the development and the operations of the Mars transportation options. We need to establish the requirements that will be imposed to meet the redundancy and reliability that will drive performance, but also determine the facilities and ground testing architectures, which is still undecided for both the nuclear thermal and the nuclear electric propulsion qualification and acceptance testing. These can and will have major implications in the resource requirements and risk posture moving forward. As example, the Space Technology Mission Directorate, the budget has included a significant long-term commitment for long-duration testing of the solar electric propulsion thruster that's being used for Gateway. We have to determine whether or not we're going to do similar architectures with similar testing of 100 kilowatt strings for years, and in what facility, and acknowledging that there is no possibility for non-condensable propellants to be used at megawatt classes for our ground demonstrations. We still need to figure out how we perform the EMI testing for 100 kilowatt class strings or combined systems, which may exceed current facility limitations. And for nuclear thermal propulsion, we need to determine the best method for acceptance testing and qualification of the crewed flight engines. We need to define the architectures for qualification of both of these NEP or NTP systems that will satisfy the safety and mission assurance needs, which may have significant implications in the resources required to execute, or even the performance based on, for example, how redundancy is mandated in the man-rated megawatt class power management and distribution systems. Many of these questions need to be addressed before an informed down select of the nuclear propulsion options. Again, understanding the cost risk and schedule risk of the future phases of development is the priority. Phase 1 is intended to be relatively quick. To be clear, we do not want to continue with more studies. We want to transition from studies to the rigorous engineering of the potential solutions we require. On the next slide is a little bit more fidelity into Phase 2. Here, after identifying the path forward, there will be a focus on component development and subsystem maturation. The objectives of Phase 2 overall are to increase the fidelity of what is required for an integrated system demonstration. For nuclear electropropulsion, that includes having facilities available to meet our requirements, something nuclear thermal propulsion has been addressing for the past year. The Phase 2 also includes the development of prototypes, risk reduction testing, and working long lead items, which further reduce the cost risk as we progress through the milestones. On the next slide, we provide additional information on Phase 3. The objectives are to demonstrate integrated systems in Phase 3, which continuously drive down the risks to an eventual flight transportation system development. For nuclear electropropulsion, this could include an Integrated System Technology Demonstration Unit, or TDU, which would be at a representative scale in a relevant environment. We would have a high-fidelity reactor design for the nuclear electropropulsion system, power system testing, and an integrated demonstration of power conversion, heat transportation, heat rejection, and operations of a propulsion system. For nuclear thermal propulsion, similarly, we would have an integrated, scalable system demonstration. On the next slide here, we must acknowledge that it has not yet been determined if there will be a ground or a flight demonstration for Phase 4, and what is required to sufficiently buy down the risk. In other words, the expectations of the risk posture and final product handoff to the Exploration Systems Development Mission Directorate has not been defined yet for Phase 4. As example, the nuclear electropropulsion system may not require a nuclear power source for an in-space demonstration, depending on the relevant environments that can be achieved through ground testing. And the nuclear thermal propulsion system may require active cooling if we want to demonstrate the burn, coast, burn environments, and so on. We do not yet know if we need to have a formal agreement between the Space Technology Mission Directorate and the Exploration Systems Mission Directorate in order to make this determination. This is because there is significant forward work to define Phase 4, which will largely be completed through the Phase 1 activities, establishing our unknowns and our risk postures, and this will be done in partnership with the Exploration System Development Mission Directorate. Throughout the development, we will continue to leverage the Department of Energy and also DARPA Draco products as appropriate. It is also yet to be determined if a flight demonstrations may have efficiencies if we combine them with other technology demonstrations, such as the Mars entry, descent, and landing technology demonstrations, or if we want to combine active cryogenic cooling fluid management system demonstrations with the nuclear thermal demonstrations. In the next slide, we summarize here that the next steps are capability gap priorities to systematically buy down the schedule risk and cost risk as the technology development transitions through the technology readiness levels. The near term for nuclear thermal propulsion is focused on the fuels and reactor designs. Subscale testing and the new near-term need for nuclear electropropulsion addresses the unknown unknowns with engineering rigor and applied to subsystem design. The midterm objectives include scalable integrated system demonstrations. The gap closure will be achieved when we have an integrated system demonstration with sufficient risk for customer handoff, and that is forward work to be defined. The last slide provides acronyms for reference. Thank you.